Okay, hello all. Welcome to this video where we look at finding the solutions to trigonometric equations, or leading towards more what we're working towards really is finding intercepts when we're graphing trigonometric equations, especially when we got transformations to them, in particular horizontal and vertical translations. One of the important skills we need to have is to find at least the intercepts, or sometimes an intersect with another graph. So the first step in doing that is we need to be able to solve. Solve for when an equation is equal to 0, or solve when the equation is equal to some other number. So first off, let's have a look at this example here, where we are given y equals 2 sine x minus 1. Find the, and this is a key word that I'll come back to later, but find the first x-intercept. So finding an x-intercept, we would let y equal to be 0. So it follows on that 2 sine x minus 1 is equal to 0, and we just use our standard algebraic process. Okay, we're using algebra to solve that, and we now get to sine x equals half. Now you could using, that's going to be one of the memorized angles. Okay, we can know, like, we've got sine x equals half. X is an angle. You used to probably also seeing in sine theta equals half. Okay, so if you're using your calculator, that would be the next step, but we know it's asking what angle gives us a sine value of half. And you could use your right hand trick rule where you bend your fingers, or you can think of the table that you memorize some values from, but we know that sine x is equal to half at the angle of 30 degrees, or pi on 6. One thing to note is this little note here, okay, that we always want to double check, is in this case it was equal to positive half, so sine is positive in the first quadrant, therefore we can still accept pi on 6 as the correct answer. An alternative to that, just over here, might have been if we ended up with sine x is equal to negative half. Space. Sine x is equal to negative half. Okay. So we have some angle that needs to give me a negative sine value. So if we remember our unit circle, when is sine negative? Well, sine is our vertical component, so all of that is positive, so we can't have that, so it needs to be some angle in the bottom half. So in that case, the first time we get around, this would be going around to pi, and then we'd have to go another pi on 6. So the eventual answer for this, the very first time that this is true, that's what it's asking by first. What is the first time this is true? What angle occurs? That's first time. Well, it's going to be pi plus pi on 6, which gives us 7 pi on 6. So there's just another alternative why it shows it's important to check what the sign was back here, and then what's the correct quadrant that'll make that true. Okay, so a couple examples. One of these might be that issue where we end up with something negative. No, we're going to end up with all positive values. Okay, so find the first solution to the following equations. Well, we've got 2 cos x equals minus root 2 equals 0, so it follows that 2 cos x is equal to root 2. Cos x is equal to root 2 on 2. Okay, what angle gives me a cos value of root 2 on 2? If you remember the table of values, or use your hand rule, when is that true? That is going to be when x is equal to pi on 4. Now, back here, this was positive, therefore cos is positive in the first and fourth quadrant, okay, and we want the first solution, okay, so it would be in the first quadrant, so x equals pi on 4 is correct. We'll have a look at example B. We've got 2 sine x minus root 3 is 0, so again using algebra, we slowly rearrange root 3 on 2. Okay, so again, what angle gives me a sine value of root 3 on 2? So sine is the vertical component, and this is getting larger, so it's root 3 on 2, so it happens to be x is going to be pi on 3. Okay. Same thing, we have a positive value. We want the first time that this occurs, and that will be first quadrant again. So this is correct. Right. Now, that was pretty straightforward. That was using our table, effectively using our tables of values, memorized angles in reverse, and we were just finding the angle that appeared in all of those cases in the first quadrant. Okay, so that was the first solution, but there's usually more than one x-intercept, and that's really obvious to see when we just do a quick sketch of any sine function. Okay, there's an intercept there, there's an intercept there, there's an intercept there, there's an intercept there, there's an intercept there. Okay. That keeps repeating on and on and on and on. But in the previous slide, we just found one. We found one. What's going on here? Well, we'll find the first. And like I said, if we kept going with this, when we use this first example here, we've got cos x equals root 2 on 2. Okay. When is that true? Well, that is true at pi on 4. Do a quick unit circle. Okay. There we go. Okay. The angle there is pi on 4. When is the next time is that true? Well, cos is a horizontal component. It needs to be positive. So not in the second quadrant, not in the third quadrant. But if I also drew in another line there, and that was at negative pi on 4, that would also be true. Okay. Or we could think of that as going all the way round. So what do we have? We have negative pi on 4 is true, that occurs. But then we also have, what's that? That's 2 pi, and then going back pi on 4, which is actually equal to negative 7 pi, 7 pi on 4, not negative. Okay. And then what happens if we, and just to draw another circle, what happens if we went around a full 360 degrees and then went up pi on 4? So we've gone 2 pi all the way around, and then we've got another pi on 4. Well, that also gives me the same, and in all of these cases I'm getting this exact same horizontal component. So this one would be 9 pi on 4. As we can see, if we keep going round and round and round the unit circle, we'll keep finding the solution. We can go around 2 pi and we'll end up at the exact same spot, and that will also be a valid solution. Okay? And then there's not only just for in that first quadrant, there's normally another quadrant, well, there actually always is another quadrant where it'll be true, because if it's positive, it's always going to be in the first and fourth, and sine, if it's positive, it's always going to be the first and the second. If you think about your horizontal and vertical components, when they're positive, when they're negative, that makes complete sense. And that's what leads us on to, because we can keep going round and round and round and round and round, we're going to get multiple solutions. And that's what this example works us through. So we work through solving this, okay, we get pi on 4. To find all the solutions, first look to see if the solution is given as positive or negative. So in this case it was positive here. Our horizontal component, cos of some angle gives me root 2 on 2. That is a horizontal component of size root 2 on 2. It is positive. We only want our positive solution to cos, therefore it occurs in quadrants 1 and 4. To find the angle in quadrant 4, we can use the identity 2 pi minus x, which gives our second angle of 2 pi minus pi on 4 is 7 pi on 4, which is exactly what I figured out there. Okay. We went, and if I redraw the diagram, make it nice and clear. Yeah, that's not a nice circle. That's closer. Pi on 4 is just that horizontal component. Okay. That will also occur. We go around 2 pi, so all the way around 2 pi, minus pi on 4. Gives us the same horizontal component, which is what we need. We need the horizontal component that was positive. So that's what that slide is describing. There's multiple quadrants where we can get the correct solution, and then if we go around the circle a whole nother time, well, shock horror, we're in the exact same spot, we get the same value. So find all the solutions to the equation tan theta equals minus root 3 for theta between 0 and 2 pi. Okay, so we've got tan theta is equal to negative root 3. Okay. So let's get a bit of that. Let's get a big one. Nice big unit circle. Okay. When is tan? This is the important thing. We have negative. When is tan negative? Well, tan is negative in the second and the fourth quadrant. It's positive there and positive there. Okay, so straight away that rules out those quadrants. My angle cannot be in there. Now, negative root 3, if we just think of first the simple form, what if we start with just tan theta equals root 3? What is the theta that gives me that? If we think of our table of values, 30 degrees is 1 on root 3, 45 would be 1, which is near, and then the second one is root 3. Tan gets bigger as the angle increases. So the ones to remember quickly are 30, 45, and 60. As tan, the angle goes up, it gets bigger, so it starts with 1 on root 3, then just 1, then root 3. Those numbers actually are getting bigger. So in this case, theta is 60 degrees, which is also equal to pi on 3 for our first quadrant. But we can't have the first quadrant because it's actually negative. So we could go around negative pi on 3, and that would give me the correct tan value. Theta is equal to negative pi on 3 for what we're used to seeing. But we need to be between 0 and 2 pi. 0 and 2 pi. And so we can't have that. We know it's going to be there. No, that up there is pi on 3. I actually will leave that there for a second. Okay. So that pi on 3 is actually going around 2 pi on 3, which to prove to you. So for the second quadrant, let's call this theta 1. Theta 1 because it's our angle that works in the first quadrant. Now tan, which is going to be in the second quadrant angle is equal to pi minus our first quadrant, and then an angle in the fourth quadrant will always be equal to 2 pi minus our first quadrant angle. Those are those symmetry identities, just rewritten a little bit from a previous exercise. So that means our angle in the second one will be pi minus pi on 3, which happens to be 2 pi on 3. And then the fourth quadrant is equal to 2 pi minus pi on 3, which is going to be 5 pi on 3. And they are my two solutions, okay, that work for that domain. So that was a little bit messy, so let me try and summarize what the strategy was. Okay. In the end, I ignored my sign at the start, okay, and found angle in first quadrant. Then I considered the sign and identified correct quadrants. Okay. And so converted, in the last step, converted theta to the correct quadrants. So that was the step, that was the process that I went through. Okay. If I ignored the sign, okay, step 1 there, okay, that would be, if there was no negative sign, the correct angle would be pi on 3. I then realized, okay, looking at the sign, well, technically that has to occur in the second and the fourth quadrants because it's negative, so let's convert it, and then converted the theta to the correct quadrants using the symmetry sim identities. And that was the process. Now, up until this point, as it says, we have looked at functions with just the standard period, so there's no dilation. Okay, so if we go back, theta, there's no coefficient to theta. There's no coefficient to x, no coefficient to x, no coefficient to x. There's no coefficient inside the trigonometric function, therefore we have had no horizontal dilation, so we haven't dilated away from the y-axis. If there is a dilation in the y-axis in play, then we must alter our domain before solving. Okay. So the process that we're going through, we wouldn't have to be clear, if we just looked at this, got it on our calculator, and sketched it, well actually it's a cos graph, so like that, okay, and then we're looking for when this angle is equal to half, so we could put in y equals half across there, and we can just go, okay, which points that cross in our domain, okay, and that would be the correct domain. Okay? That would be correct domain if we just did it graphically. And we could just go, okay, between 0 and pi, and it might be that, and this graph I haven't even checked to see if it's right, but it could be that pi is there, and then which ones are correct? Well, that one's correct, that one's correct, that one's correct, that one's outside the domain, so it's no good. So you could do that on your CAS, completely fine, you don't have to alter the domain. But if you don't have access to your CAS, or you're going about it algebraically, okay, we need to consider this 2 is having an impact. Okay. So we have to change what is our given, we call this our given domain, okay, and we have to change it to a working domain when working algebraically. Now the way you do it is multiply the domain by the n value. Okay, so we've looked at the general form before. this number inside here, that's called our n value. So whatever our n is, it could be 3, it could be 2.2, whatever it is, whatever our values of our given domain, to convert to the working domain, okay, we multiply by the given domain by n, and that will give us our new domain, working domain. So that when we then start solving the problem, algebraically, we know which values we can accept and which values we have to discard. Okay. So in this case, cos of 2 theta is equal to half. Okay. So if we then did, and this isn't shown on this slide, but the step in between here, where do we get this pi on 3? Okay, that's turned into cos 2 theta is equal to the inverse cos of half. Okay, so that then turns into 2 theta is equal to pi on 3. What angle gives us a cos value of half? It turns out to be pi on 3, and also 2 pi minus pi on 3. Okay, in the fourth quadrant. Okay, and we can accept that pi on 3, it's in the first quadrant because our working domain is 0 to pi. Okay? And like always, when you're first seeing this, when all the steps are already shown, it can be a little bit confusing, so stick with me and we'll go do a work example in a second, and that might really help. Okay, so we got, to get to this step, okay, was doing this, solving 2 theta equals inverse cos of half. Well, that's pi on 3, 2 pi minus pi on 3, it's also 2 pi plus pi on 3. It keeps going. Okay, 2 pi plus pi on 3. Keeps going with that pattern. There's solutions on and on and on and on forever. Which ones do we actually accept? Well, we look at our now working domain. Okay, we can only accept things between 0 and 2 pi. Well, pi on 3, that's good. 2 pi minus pi on 3, that's just a bit less than 2 pi, so that's fine. 2 pi plus pi on 3, well, is obviously bigger than 2 pi, so we have to scrap. Okay? And that's what this box here is talking about. And then we just, again, still solve with algebra. 2 theta equals that, so this should be actually, there it is. Oh yeah, that's 2 theta is equal to that, and then divide by 2 both sides, so we get theta equals pi on 6 and 5 pi on 6. And if we look at those now that we have theta, are they also within the given domain? And yes, they are. They are completely fine. So you essentially get 2 checks. Right here, solve the equation sine 2 theta is equal to half, or 0 between until it's getting late. Solve sine 2 theta equals half for theta between 0 and 2 pi. Okay, so our given domain is 0 to pi. Okay. Our n value is, in this case, 2. So it follows on our working domain is 2 by 0 and 2 pi. So we're multiplying our n by our given domain, so we get 0 and 4 pi. Cool, so that's our working domain, and what we'll use when we're doing our algebraic check. Okay, so if we have sine 2 theta is equal to half, it follows on that 2 theta is equal to inverse sine of half. Okay, so 2 theta is equal to. Okay, so what angles give me a sine value of a half? So when is my vertical component half? That will be at, my brain work, vertical component, that will be 30, yes, 30 degrees, which is pi on 6. Okay, so pi on 6 works. There's multiple solutions we need to think. Okay, we need a vertical component. Need a vertical component of size half. What are angles that make that work? Well, that one, pi on 6. Also, this one over here, pi on 6 up from that side, which is the same as pi take away pi on 6. When else? Well, if we go all the way around the circle back to our original one, that's 2 pi plus pi on 6. And if we kept going, and I'm just doing this to demonstrate that it's over and over and over again, we would have 3 pi minus pi on 6, and it keeps going and going. That would work. But this is when we use this is when we check, this is when we use our working domain. Check. So we needed between 0 and 4 pi. And it's actually good that I kept going on and on and on, because that's between 0, that's fine. That's fine. 2 pi plus pi on 6 is still less than 4 pi. 3 pi minus pi on 6, that's fine. So I actually need to keep thinking about this. What happens if I did a third revolution? So I go around, once is 2 pi, oh sorry, do a full second revolution, is 4 pi plus pi on 6. 4 pi plus pi on 6 would get me back there to the green one. And then another pi, so that would be 5 pi minus pi on 6. And again, it goes on and on and on and on. Okay, but just to demonstrate, that's why I kept going. 4 pi plus pi on 6, is that in our working domain? No. So that's no good, and then that's definitely too big. That's no good. So what are we left with? We're left with 2 theta is equal to pi on 6, pi minus pi on 6. 2 pi plus pi on 6, that is the same as 12 pi on 6 plus pi on 6, so 13 pi on 6. Look at that. Okay. And you'll get very good at adding and subtracting whole pies and fractions of pies, and making common denominators in your head. You can always do it by hand if you want to, or work it out on paper, but you'll get to that stage. 3 pi minus pi on 6, 3, 18 minus 1 is 17 pi on 6. Divide by the 2, so we're left with theta is equal to pi on 12, 5 pi on 12, 13 pi on 12, and 17 pi on 12. Okay? And then at this stage, okay, we can also check with original domain. Okay, and that's good, that's good, that's good, that's good. They're all good. They're all between 0 and 2 pi, so that's fine. Now this raises the question, well, if we can check at the end with the original domain, why do we even bother with the working domain? Why? Okay, well, it just adds a little bit of efficiency. It's really easy to find the working domain. You're literally multiplying by your n value. So that's not very hard. That's super easy. Okay. The advantage comes from, well, once we're checking with our working domain, well, I got rid of these, okay, these 2 solutions, and I could have kept going. So one of the advantages with working domain is I don't have to guess how many solutions. Once I find one that doesn't work, well, I stop, because anything larger than that is also not going to work. And 2, I could have done this. I could have gone, okay, 6 solutions, I'll at least estimate at least 6 solutions, and then I'll check them at the end. Is that if I did those 6 solutions, I'm going to have to do 6 times these factor additions. Okay, and then I'm also going to have to do 6 times dividing by 2, so there's another 6 times of doing something. So we're doing, I guess, 12 extra operations to check at the end versus doing one operation finding the working domain and then cutting them off as soon as we get to them. So that's why we do the working domain. It adds a bit of efficiency up front, especially there's going to be some questions where there's going to be 8 correct solutions. Okay, you just keep going until you max out your working domain. You can do this all on your CAS, okay, shown there on that slide, again using the given symbol. It's really hard to see, but it's that vertical up and down symbol, okay, being shown how to find that on previous slides. If I remember correctly, I don't have my CAS with me, but I think it's Control and equals. Brings up the option for one of those. Just the straight up and down vertical line, such that all given. There is a whole bunch of ones for you to practice on your CAS. Okay, take note, you can use theta to solve, but X is quicker, so it's preferred. And that's also handy, like we've looked at in gallery graphs and functions and polynomials and all of those topics. As soon as it comes to graphing, our variable needs to be X if we want to graph it. And especially if you're defining, okay, if you're going to define a function because you've got to do lots of things with it, you want to define it, okay, define as a function of X, not a function of theta, because it's going to make graphing a whole lot simpler. That's it for this exercise. Like always, if you have any questions, ask in class, ask via email. Send me something through Compass, completely fine. That should be it, and see you all in class.